In this worked example video, I'm going to show you how we analyse a circuit. And I'm going to demonstrate the physics analysis strategy that we would like you to use throughout this course. So here is our circuit. First step is to model it. For a circuit, I always like to start by drawing a really large circuit diagram. This is because we'll need to make lots of annotations to explain it. I also like to have everything along the top as much as possible, so let's rearrange this. Here we get the 3-volt battery, and then it splits, and along the top, which is this bit over here, we have the 1.5-volt battery and the 10 ohm resistor, and then down the split we have the 4 ohm resistor and then it goes back around here. So that is the same circuit, we've just stretched the wire. We're assuming here that everything is an ideal component. Let's label our variables. Let's call that V1 equals 3 volts, V2 equals 1.5 volts, that's R1 equals, that's 10 ohms, and R2 equals 4 ohms. So you notice I've given symbols to all the numbers. That's because we should always do our calculation in algebra form, and we're going to need symbols. Usually the best place to say what those symbols are is your model diagram. Okay, so that's our model. We're assuming these are all ideal components, so there's ideal voltage sources, so there's no internal resistance. We're assuming the wires have no resistance. Now let's represent the whole thing. For a circuit, that means sketching charge, current, voltages. So let's have a current here. I draw this with a thick arrow so I can show how wide it is. I'll call that I1. And that's going to have to split at this junction. So we'll have thin arrows to show that it's split. And we'll call that, I2. And a thin arrow down here, I3. Now I'm not quite sure what direction the current is going to flow through here. I've shown it flowing that way, but it might go the other way around, in which case when we do the calculation we'll just get a minus value for I3. So just guess if you don't know. Right, that's the current. Now let's think about voltages. What I like to do is a sketch showing the voltage as you go along this top line. So let's say the voltage starts here. Now as you go through a voltage source, the voltage must go up by 3 volts. It then stays flat all the way along the wire, and then here it goes up even further by 1.5 volts. Now we hit a resistor. Now the current's going this way through the resistor. Current always flows from high voltage to low voltage, so that means the voltage must drop as you go from here to here. It's going to drop and then go off. And we know that that end here is connected by wires to here, so these two must be at the same voltage. That's the top branch of the circuit. How about the bottom branch of the circuit? So we've got the voltage along here, and it goes along. And then, of course, the current's going this way. Current goes from high voltage to low voltage. It must drop. And this voltage is the same as that. And this voltage is the same as this. Okay. Another thing I like to illustrate is which parts of the circuit must be at the same voltage. So all these sections around here are joined by wire. So this is all... everything from there is going to be at 1 voltage. That's the lower voltage here. And this region over here, and that bit down there, is going to be another voltage, this voltage over there. Okay, so that's a representation. Let's now check it for self-consistency. If you've got the current flowing this way, the voltage drops from there down to there. And we know the voltage here must be lower than the voltage there because it's the case here. So that's consistent, and we've drawn the currents so that there's a constant current all the way around there. So there's also going to be I1 here, I1 there, this is going to be I3 through there, and I2 over here. We need to make sure that current doesn't go missing everywhere. So if you've got I2 going through here, it must be I2 all the way down there. If you've got I3 along here, it's also I3 over there. And the current into this junction has to equal the sum of the currents out. So that's self-consistent. The voltages do seem to end up back where we started from. If we had the current going the other way through this resistor, then that would go up. And in that case, we couldn't get it to work out. But in this case, it all seems to kind of fit. Okay, so now the next step is usually to have a quick estimate of what sort of values we're going to get. We've got voltages of a few volts, resistances of a few ohms, so that means currents are going to be of order a few amps. So it might be 0.5 or 2 or something like that. This estimate is a way of checking our answer. It means we know we're expecting currents of a few amps, and if in the end we stuff up the algebra and get a current of 1,000,000 amps or 10 to the minus 5, we know we're wrong. Okay, so that's our model. We've represented it. We've checked it for self-consistency. Now, if necessary, we can do some calculations and actually work out what the currents are going to be. And the way we'll do this is using Kirchhoff's laws. So Kirchhoff's two laws. One law is the junction rule, and it says that at any junction, current in equals current out. So that's telling us that at this junction, current in is I1 equals the current out, which is I2 plus I3. And we'll call that equation 1. Now we can use Kirchhoff's second law, which is the voltage law. This means if you go around any loop, you must end up back at the same voltage you started at. So for our first loop, let's go along here, along there, and back round. That's our loop 1. It's often good to mark the loops on your diagram. So what happens as we go loop 1? Let's start here. As we go through this voltage source, the voltage increases by V1. Voltage stays constant all the way along here, all the way along there, all the way along there. Then it's got to drop as it goes through this resistor by I3R2. So this is telling us V1 minus I3R2 equals 0. So as you go around that loop, you come back to where you started from. We'll call that our second equation. How about our third loop? There are two other possible loops we could use. We could go all the way around the outside, or we can go around this little loop in the middle here. Let's go all the way around the outside. We'll call that our loop 2. So in this case, we're going to go up by 3 volts here, up by another 1.5 volts there, down by I2R1 there, and then the rest is wires, and so no change. So that must come to 0. So we've got V1 plus V2 minus, not equals, minus I2R1 equals 0. And that's our third equation. So we've got 3 things we're trying to work out, the 3 currents, and we've got 3 equations, so 3 equations, 3 unknowns, thus we can solve. We could, if we like, do our third loop. Just go around here. But you'll find that that's just going to tell you things we already know. We've already got at least one loop that goes through every component, so we've got enough loops to solve the problem. Okay, so now it just becomes maths as we solve this. Notice that I've done everything in the form of algebra, using symbols. I've not substituted numbers in. We'll substitute numbers at the end. That's always good strategy because it gives you more ways to check your answers. Okay, so what are we going to do? Well, we can use equation 2. We can rearrange that. That comes as V1 equals I3R2. So we get I3 equals V1 over R2. So V1 is 3 volts, R2 is 4 ohms, so that's, now we can put the numbers in. So 3/4 of an amp. It's always important to check our answer. First of all, note that's 3/4 of an amp is close to an amp or a few amps, so that's consistent with the number here, so it's numerically plausible. How about the units? Well, we've got current equals voltage over resistance. We know that's what normally happens from Ohm's law, so that means the units make sense. How about functional form? What this is telling us is if we make the voltage bigger, the current gets smaller, which seems to make sense, and a bigger resistance makes the current less. If you had no voltage, there'd be no current. So it's the functional form is plausible. Okay, so that's given us I3. How about I2? We can get that from equation 3. Let's rearrange that. So we get V1 plus V2 equals I2R1. And so we end up with I2 equals V1 plus V2 over R1, which is, that's 3, it's 1.5, so it's 4.5 volts over 10 ohms equals 0.45 amps. Check. You should always write down that you're checking so that we know you're doing it. Once again, that's numerically plausible. The units, once again, is volts divided by resistance, so that works. Functional form, once again, if there's no voltage, you've got no current, which you kind of hope would make the sense, so the functional form looks pretty good. So this all passes a test and are plausible. We've got this for current and that current. We can then use equation 1, and we get that I1 equals I2, which is 0.45 amps, plus I3, which is 0.75 amps. So that equals 0.45, so that's 0.8, 1.2 amps. Again, numerically plausible. So there we have a complete analysis of this circuit.